What is the ATLAS experiment at the CERN Large Hadron Collider?
So the ATLAS experiment is probably the quickest way to grasp what it's for is that it's the highest resolution, highest bandwidth digital camera that we know how to build, and it's designed to photograph what happens when these protons collide at the Large Hadron Collider. And we go to a lot of effort to make these protons collide at the highest energies we've ever had. So when they collide, we want to know as much about the results of that collision as we possibly can. And that's what ATLAS is there to do. And I should say, also CMS, our friendly rivals, diametrically opposite on the ring. They're what we call general purpose detectors, designed to just see what happens when these protons collide, basically. And they're sort of cylindrical structures that surround the beam, and the two beams and the protons collide. To be honest, most of the protons miss, right? But some of them collide in the middle. The rest go around and have another go. And these cylinders, the beam goes through the kind of axis of the cylinder. They collide in the center of the cylinder, ideally. And there are kind of concentric cylinders of different technologies then around that. So there's a silicon pixel and tracking detectors that will record the path when a charged particle goes through. They're semiconductors in general. So the semiconductor is almost ready to conduct electricity, but a very small perturbation, such as the passage of a subatomic particle with some charge, will move an electron from the insulation band to the conduction band, and then carry the electrical current, which you can read out and then tell that the particle went by. And there's a magnetic field around that, which bends the particles according to the momentum. So if you can join the dots on a track of the passage of a particle, then you can measure the curvature and you can measure its momentum. And then around that, there are calorimeters, which measure energy, as you would guess from the name, I guess, which are designed to essentially stop everything. And as it stops, it decelerates and it gives off photons. And if you're smart enough in the way you count the photons, then you can work out the energy of the particle that you stopped. And then around that, there's the most obvious thing. If you look at a picture of one of these detectors, the most obvious thing is always the muon system. It's only designed for one particle. It's the biggest bit of the detector. It's the outer layer, and it's the biggest bit. It's designed to detect this one fairly rare particle, the muon. It's like an electron, only heavier. It's they're produced in cosmic rays, but they're not very stable. So often they're a sign that something interesting happened in the collision. And because they're like the electron but heavier, they don't get stopped by the calorimeters because they're too heavy to be decelerated by hitting the electrons in the material, and they don't interact with the strong interactions, so they don't get stopped by the nuclei much either. So they kind of punch all the way through, but they're charged, so you can measure them on the outside of the detector as well. So that's basically what they do. And that covers basically all the standard model particles except for neutrinos, which you can't measure at all. That you can measure them if you have billions of them in a huge detector, and there are other experiments that do that.
Right.
But if you create one in a collision, your chances of seeing it essentially zero. So we can kind of deduce that they were probably there by the fact that the energy doesn't balance up, the momentum doesn't balance up transverse to the beam. So that's why they're cylinders; they completely surround the beam. So, yeah, so that's what they do. And coupled to that, of course, is a whole bunch of very fast readout electronics to try it, because we have 40 million bunch crossings a second. So 40 million bunches of protons per second, every 25 nanoseconds, passing through each other. And in each one of those is of order 100 proton-proton collisions. So we've got 4,000 megahertz-ish of proton collisions coming at a 40 megahertz rate with a lot of data, many gigabytes per collision of data. So doing a data reduction job on that and trying to weed out the rubbish as quickly as you can and keep the things you care about is, there's basically an office block full of electronics next door to it trying to do that as well. And then it gets, the data gets farmed out all over the world on the computing grid, and it ends up on my laptop, basically.
Okay, there are a lot of questions there, a lot of thoughts. One thing that just comes to mind is that neutrinos are quite interesting, have a fascinating history, but you mentioned how hard they are to detect.
Yeah.
I think there are like billions or trillions of them passing through us, each of us, from the sun
Yep.
at any given moment, which is just pretty amazing. And they hardly ever interact with us. They build these huge, obviously, as you know, heavy water containers deep
Yeah.
in mines
Yeah.
to detect them. And it still happens pretty rarely.
Yeah, that's right. No, they're amazing. There's the kind of famous picture of a guy in a rowing boat going around the Super Kamiokande detector in Japan, which it's built underground to do this. And the next big experiment in the US actually is going to create a neutrino beam and fire it to South Dakota from Illinois. It's called the June experiment, and it's going to be pretty cool. And they will be able to measure some small fraction of those neutrinos in that beam. But with Atlas, we have no chance.
And then continuing to talk for a minute about detectability, you mentioned that the muons are heavier than electrons.
Mm-hmm.
They're unstable. They don't interact with the strong force. Maybe
Mm-hmm.
this again just presages some of the things we might talk about when
Yeah.
we get to the Higgs boson. But how do these features, so weight or mass, instability, interaction, how do all of these relate to detectability more generally?
Sure. So, first of all, the lifetime, the fact that they're unstable doesn't really matter to Atlas because they live long enough to travel hundreds of meters. So, from our point of view, they're essentially stable. I mentioned that they're not stable. It's relevant that they're not stable because we don't see them in nature. We don't see them appearing in atoms. I mean, we see them produced in the upper atmosphere when a high energy particle hits the upper atmosphere from space, but they don't live very long. So they're not like electrons you find in everyday material. You don't find muons in everyday material for that reason. It doesn't really affect their detectability from our point of view. The detectability comes about, first of all, they have electric charge, which is a good thing for detecting them. And that means they show up they will show up in our silicon detectors and things. The fact that they're heavy and don't feel the strong force have two different effects. So you got to think of the calorimeter as it's atoms, it's dense material because it's designed to slow things down, to stop things. But essentially, an atom is a bunch of candy floss surrounded by a kernel, a bullet, or something. It's let's say a steel ball bearing surrounded by candy floss. Now, the candy floss is the light electrons, and the ball bearing is a really heavy nucleus in the middle. And the nucleus interacts via the strong force. It experiences the strong force. The candy floss only feels the electromagnetic force. When an electron hits that, it's only the size of a grain of sugar, so it will interact with the candy floss and be stopped by the candy floss. When a muon comes in, it's more like a bullet. It's because it's heavy, and it just punches straight through the candy floss. It doesn't care about the candy floss. There are other heavy particles called hadrons, pions mainly, that will do the same, except that they also feel a strong force, so they have got more chance of hitting the ball bearing in the middle as well because they're interacting by the strong force. The muon doesn't have that, so it won't stop. Basically, it will just punch all the way through. If it's really unlucky, it might hit one of the ball bearings, but very, very rarely because it's not feeling the strong force. So it will just bang right through. But if it bangs right through the calorimeter, then it will emerge on the other side, and it's still got electric charge. So we measure the path of it on the outside as well, and we never stop it. We never stop the muons, but we can at least we can measure their trajectory and their momentum. And if they get through the calorimeter, then they pretty much must be a muon because that's the only thing it would do. It would do that.
Two last things I wanted to get to just with the Large Hadron Collider, and one is you mentioned CMS,
Yeah.
your friendly rival, and the Large Hadron Collider and CERN in general. The Large Hadron Collider is a physical object. CERN is a group of people, but they're both respectively huge. You mentioned that CMS is on the other side of this many kilometer long collider. Just how does the Large Hadron Collider work on a sociological level. I mean, you have thousands of people working on it. There are multiple experiments going on,
Right.
different groups. Just I don't think people, I certainly don't understand how it all works exactly.
I guess the key concept is the collaboration. So each of these big detectors is run by a collaboration of thousands of physicists from dozens of countries, and different universities and things around around the world. So it's not like I go out there with my PhD students and postdocs and do an experiment and bring the data home. It's that we built some of this thing in London, and other people built other bits of it all around the world. We take it all to Geneva, we put it all together, it all works together, and we all get all the data from it all the time. So it's a very collaborative enterprise in that sense. All the data from everyone's bit of Atlas is shared, even though Atlas was built by different people all over the world and coordinated at CERN, obviously, to make sure it all functions properly and works, which is by no small challenge. It's a super high-tech jigsaw that has to all fit together perfectly. And then, so Atlas is run by a collaboration of literally 3,000 people. If you look at our papers, it's got 3,000 people on the author list of every paper. And the reason for that, I mean, I must admit there are papers out there that I haven't read that have got my name on. And that's because I made significant contributions to the experiment, and so, and I'm therefore a member of the collaboration. And it's not a perfect system actually, but it's better than if we didn't do that, we don't even put them. They're all alphabetically as well, so no one gets any individual priority or anything, which confuses the hell out of university administrators and everyone else. But it's the only way we can think of being sure that it'll work, because we don't want these rivalries to take over and split the collaborations. So, clearly there are a lot of egos and rivalries involved, and everyone's got to get their career, make their own career, and get recognized for the work they do somehow. So I'm not saying it's a solved problem, but the reason there are such big author lists is because it takes all those people to make the damn thing work, and then you really have to. You don't want to spend. There's enough work to do making it work, collecting the data, analyzing the data, making sure the results are right and publishing them, without spending another equal amount of time arguing about who actually goes on the author list and in what order. So we don't do that. But CMS is a separate collaboration. So in a way, it's scientifically, it's a guard. First of all, that each experiment's made different technology choices, so it's risk mitigation. That if one of them had made a bad choice, then the other one hopefully would still work, and the LHC would not be firing away with no detectors working. So that luckily they both did work, but they do both have different strengths and weaknesses in some places. Also helps you avoid groupthink at some level. You have some people over there keeping you honest, and may come up with some fancy idea that you hadn't thought of, and there's a room for innovation and the stimulation of innovation in that, I think, which is beneficial. But and to be honest, right, Atlas has got a huge if you look at the map, Atlas is near the main laboratory. CMS is 15 kilometers away in the French countryside. So in the end, the social interactions mostly happen on the main lab in restaurant 1 or 2 on the CERN lab, and you try and there's a lot of gossip there, and people really do. I mean, it's friendly rivalry, okay? Mm-hmm. When we were on the verge of discovering the Higgs, people were pretty tight-lipped, I have to say. And you got to remember,